I hope you are doing okay. So this is PH110 physics. We're still looking at units and measurement, and in this topic we'll concentrate on dimensional analysis, simply DA, abbreviated as DA, dimensional analysis. So in the previous videos talked about converting units from one system of measurement to the other, converting within the system, of course, using the chain linking conversion. And in this video we'll simply concentrate on dimensional analysis. Okay, so by definition, dimensional analysis is simply the study of the relation between physical quantities based on their units and dimensions. The study of the relation between physical quantities based on their units and dimensions. Okay, so we'll be dealing with the physical quantities, studying their relations between their units as well as dimensions. Now, the physical quantities that we will concentrate on under dimensional analysis are the basic physical quantities or the fundamental physical quantities, and in particular we'll be talking about so it's mass, length, and time. These three fundamental physical quantities are the ones we'll be concentrating on. Okay, so now we should know the dimensions of mass, length, and time. So for mass, if we write it in square brackets like that, so we are saying dimensions of mass equals, so for dimensions of mass we use capital letter M. Okay, so you should take note of that dimensions of mass we use capital letter M, dimensions of length we use capital letter L, and dimensions of time we use capital letter T. So we're using square brackets that to say dimensions of mass equals capital letter M, dimensions of length equals to L, dimensions of time equals to T. Okay, so even when we have derived quantities, it is possible to find their dimensions. So when we have derived quantities, for example, if we talk about what? Velocity, it's possible to find the dimensions of velocity itself. So I know that velocity is equals to what? Of course, it's displacement over time. Then this displacement is measured in what? Of course, displacement we use what? We use meters, so this is simply length. Displacement we use meters, so that is simply length. And this is simply time itself in seconds, that's length in meters. So we now know the basic quantities that make up velocity. We have length over time. So for length, we know that the dimensions for length we use L there. So we say L over dimensions for time we use what? It's capital letter T. So this side you can even say dimensions of what? Velocity V like that equals to L over T, but we shouldn't leave it like that. So you can agree with me that dimensions of velocity equals to L. This one can be written as L multiplied by what? 1 over T, like that. Then you know that if you have n number, let's say a to the power negative n, that is simply 1 over a to the power n. Or if you have a to the power negative 1, meaning that is 1 over what? 1 over a. So we can write 1 over t as t to the power negative 1. So we proceed by saying dimensions of v equals to L t to the power negative 1, like that. So you can try to do the same for other physical quantities. For example, force equals to ma, then you break down that into its basic physical quantities. Of course, you find its mass, length, and time. Okay, then from there we can proceed to what we are calling the principle of homogeneity of dimensions. So principle of homogeneity of dimensions. Okay, so as we'll be solving questions under dimensional analysis, even the principles we'll be using are those the what we call them principles of homogeneity of dimensions. So under this we have two statements or two principles we should know. Okay, then the first one will say an equation is dimensionally correct if the dimensions of all the terms on either sides of the equation are the same. So the dimensions of the terms on either sides of an equation should be the same. For example, if we talk about this same velocity, we know we have what? Velocity equals to LT, the dimensions of velocity equals to what? LT to the power negative 1, like that. So this side, if we check, velocity is measured in meters per second. Velocity is measured in what? If we check the left hand side, dimensions, velocity is measured in meters per second, like that. Then for meters, that's what? Length. Second, it's time. So on meter length, we can even use L there for dimension, then over T. Then L over T, you agree with me that it's LT to the power negative 1. So this is what we have found on the left hand side. And on the right hand side, we have LT to the power negative 1. So this is what we mean by dimensions on other sides of the equation should be the same. So let me repeat the statement again. So we are saying an equation is dimensionally correct if the dimensions of all the terms on either sides of the equation are the same. Or if we use, for another example, let's say we talk about final velocity equals to initial velocity plus acceleration times time. V equals to U plus at. Final velocity equals to initial velocity plus acceleration times times time. Yes. So for velocity, we know that this is measured in what? It's meters per second, of course. Then for this is also velocity, initial velocity. It's meters per second. Then that's acceleration, so plus. So for acceleration, we know it's meters per second squared. Then for time, it's what? Second only. So this side we have meter per second equals to its meter per second, then plus. So as you can see, there is second squared second, so meaning just remain with meter per second. Then meter per second, this is what? Velocity. So, and the dimensions of velocity, remember it's LT to the power negative 1. So LT to the power negative 1 equals to, even there meaning we have LT to the power negative 1 plus LT to the power negative 1. So the dimensions of all the terms are the same. So this is the first term, second term, third term. So 1, 2, 3, all the terms have the same dimensions. So we can say this equation is dimensionally consistent or dimensionally correct. Okay, so that's what we are talking about. So that's the first principle. Then the second one, let me just proceed to next. Okay, so the second one, we are saying that we can multiply or divide physical quantities with the same or different dimensional formulas at our convenience. However, no such rule applies to addition and subtraction, where only the same or the like physical quantities can be added or subtracted. So here what we are saying is this. Let me use the same example for velocity v equals to u plus at. Okay, so we are saying that we can multiply or divide physical quantities with the same or different dimensions. So physical quantities with the same or different dimensions can be multiplied or be divided, but that do not apply to to addition and subtraction. So for addition and subtraction, it's only where like physical quantities can be simplified. That's where we deal with only like physical quantities. So if you see physical quantities being added, just know that they have the same dimensions, or they are being subtracted, just know they have the same dimensions. For example, there we have acceleration and time there. So for acceleration itself, let's talk about acceleration. No, acceleration, it's meter per second squared. Then its dimensions, let's say dimensions of what? Acceleration will be what? This is meter, that's length, so we use L, then time, so over t squared, second its time. So dimensions of acceleration equals to, so L over t squared, you agree with me, to be L t to the power negative 2. So these are the dimensions of what? Acceleration there. Then what about time? So for time, we know it's t, only t. For dimensions of that t, it's just capital letter T. Then we are multiplying acceleration and t. So these have different quantities like that. Yes, so they can be multiplied or be added. They have different dimensions. Okay. Then when we talk about addition and subtraction, we only add those with the same physical quantity. So here, this is u, that's at, u as and at. So we have v equals to u plus at. So there on at, this is acting as one term, and u one term, this one term. Okay, so on v, we said it's meters per second, right? U meters per second, then plus acceleration is meter per second squared. They multiply by what? Second. Okay, so meter per second equals to meter per second plus, that's 2 meter per second. So as you can see, meter per second, meter per second, meter per second. These two are being added. So that tells us they have the same physical what? They have the same dimensions. So for this one dimension, it's LT to the power negative 1 equals to LT to the power negative 1 plus LT to the power negative 1. Same dimensions. As long as they are being added like that, you know that when you simplify them, use dimensions, they should be the same. So you see how apply this when solving questions. So I hope you have taken note of the two principles of what? Homogeneity of dimensions. Okay, then let's talk about the applications of dimensional analysis, or simply the uses. Applications, application, or simply uses of dimensional analysis. Application or uses of DA, dimensional analysis. Okay, so first thing we should know is that dimensional analysis is used to find the units of a physical quantity in a given system of units. So to find the units of a physical quantity in a given system of units. So it's possible to do that too. We'll see when solving questions. So we're saying to find the units of a physical quantity in a given system of units. Okay. Then apart from that, another use is to find the dimensions of a physical constant. To find the dimensions of a physical constant. So we know that, for example, we have a formula for what? Kinetic energy is equals to what? It's 1 over 2 mv squared. That's the formula for kinetic energy. So you can say, actually, when deriving this formula, will be equal to, initially this 1 over 2 is simply a constant. So you can say k mv squared. So it's possible to find the units and the dimensions of that k, that physical constant. We can make k subject of the formula and find its units or its dimensions. It's possible to do that. Okay, so let's say for kinetic energy, for simplicity, let me just use k equals to, actually let me use km. Okay, kinetic energy, just like that, equals to K mv squared. Okay, then meaning we divide by mv squared over mv squared, so that we remain with K equals to kinetic energy over mv squared. After that, we can substitute with the units for what? Kinetic energy there for mass, velocity, and so on. Then we find it there what? The dimensions of K as well as its units. Okay, so we have talked about two applications. Number one, to find the units of a physical quantity in a given system of units. Then number two, to find the dimensions of a physical constant. So we'll solve more questions. We'll solve questions so that we can clearly understand what we are talking about. Okay, then the other one, number three, the third use or application, is to check the correctness of a given equation. For example, the same way we did with this formula for velocity final equals to initial velocity plus at. So if we find that dimensions of all the terms on either sides of the equation are the same, we say that this equation is dimensionally correct or dimensionally consistent. So that's another use of dimensional analysis. So I'm saying it's to check the correctness of a given equation. So when we find that, we can even conclude that that equation is actually dimensionally correct. Okay, then the other use is to derive formulas. So we can use dimensional analysis to derive what? Formulas. To derive formulas using dimensional analysis. So we look at this one. How can we derive formulas using dimensional analysis? Look at that one when solving questions. Okay, so these are the uses. Can proceed to something else. So we have talked about some of the uses of dimensional analysis. Then proceeding to something else, of course, dimensional analysis has limitations. So what are some of the limitations of dimensional analysis? Okay, so the first thing which we should know is that dimensional analysis does not give the value of the constant. So dimensional analysis does not give the value of a constant. Let's say when deriving the formula, we'll be using a constant K. Find that the formula for kinetic energy will be equals to K mv squared after deriving. So we can't guess the value of K. We can't know anything about the value of K using dimensional analysis. Unless more information is given, that's when we can solve for K, or maybe if K itself is given. Otherwise, dimensional analysis does not give the value of this constant. Okay, then rather than that, dimensional analysis is not applicable to logarithmic, exponential, and trigonometric functions. So it's not applicable to what? To logs, to exponents, and the trig functions. Yes, so this one does not work for logs, exponential, and trig functions. So we can't even use dimensional analysis to derive formulas of what? Logs, exponents, and trig functions. For that, dimensional analysis is not applicable. Okay, then rather than that, dimensional analysis gives no information whether a quantity is a scalar or a vector. So gives more, does not give any information whether the quantity we are dealing with is a scalar or a vector. So dimensional analysis doesn't tell us that whether the quantity we are dealing with is a scalar quantity or a vector. Does a quantity only have magnitude, or does it have both magnitude and direction? So dimensional analysis doesn't tell us that. So that's another limitation. Okay, then the other limitation which we can talk about is that dimensional analysis can't derive equations with more than one part. So dimensional analysis can't derive equations with more than one part. For example, this same equation V equals to u plus at. V equals to u plus at. Dimensional analysis can't be used to derive that equation unless, because it has more than one part this side, first part and second part, like that. Unless equation such that f is equals to what? MA, yeah, only has one part, doesn't have two parts, like V equals U plus AT. Okay, so even this equation, yeah, it can be derived using dimensional analysis because it only has one part this side. Otherwise, if you had plus something this side, no, dimensional analysis can't be used to derive such formulas. So these are some of the limitations of what? Dimensional analysis. Yeah. So for the last one, we are simply saying equations should be of product type in order to derive them, not whereby we have difference type or addition type. No, it won't work. Okay, so these are the important things about dimensional analysis that we should know. Number one, definition. Apart from definition, the principles of what? Homogeneity of dimensions, the uses or simply applications, and the limitations of dimensional analysis. So make sure you take note of that. Okay, so apart from dimensional analysis, let's also talk about some other concepts. Significant figures. So solve questions later. Significant figures. Okay, for significant figures, you can say it's just more like a revision. We can talk about the rules for significant figures. Okay, so the first rule which we should know is that all non-zero digits are significant. All non-zero digits are significant. Those are non-zero digits. All these are significant, and so on. These are non-zero digits. We say they are significant. Then the second one, we are saying all zeros occurring between non-zero digits are significant. For example, if we say 1, 0, 0, 2, another one, let's say 2, 0, 5, 0, 8. So these zeros are occurring between non-zero digits. We say these are significant. So in this number, how many significants are there? So simply count 1, 2, 3, 4. So we have 4 significant figures. That number we have 1, 2, 3, 4, 5. So that's 5 significant figures. Otherwise, if we have something like 1, 0, 4, 2, 0, 0, like that, then how many significant figures in this case? So in this case, it's only this 0 which will be significant. These two zeros are not between non-zero digits because you don't have a number that side. Hence, we just count 1, 2, 3, 4. We have 4 significant figures. These two are not significant. Okay, those are the first two rules we have talked about. Then the second one, we are saying that if a number starts with a decimal, or the zeros on the left side of the first non-zero digits are not what? Significant. But all the zeros on the right are significant. For example, if we have 0.000124, like that, and another one, let's say 0.003010. Okay, so we are saying if a number has a decimal point like that, then these zeros on your left, before any other non-zero number are not significant. So say these are not significant. Then these zeros on the right, like this 0, this is a decimal number. Then this 0 on the right, after you have the non-zero digit numbers, any zeros that follow will be significant. So for this one, how many significant figures? The zeros won't be counted, just 1, 2, 3, 4. So for this one is 4 significant figures. Then for this one, due to that number, even that one, 0 at the end will be significant. So we have 1, 2, 3, 4 significant figures like that. So this is what we mean when we say that if a number starts with a decimal, all the zeros on the right side of the first non-zero digit number are not significant, but all the zeros on the right are significant. So this is what we mean. Okay, hope you get that. And you can proceed to talk about another rule we use to determine significant figures. So the other one, we are saying that if a number has an integral part and a decimal part, all zeros in the number are significant. So this is what we mean. For example, if you have, let's say 20.10, 20.10 like that, and another one, let's say 50.00. Okay, so this first part, the whole number part, is the one we are calling the integral part, and this is the decimal part, this side. So if we have an integral part, the whole number part, so for the whole number part, we don't have a 0. Yes, for the whole number part, you don't have a 0. You have digits like that. 2, 0. In this case, you simply count all the numbers to be significant. So for this one, we say 1, 2, 3, 4 significant figures. 4 significant figures. And for this one, simply 1, 2, 3, 4 significant figures. Otherwise, if it was just like 5, 0, 0, 0, 0, for this one, you simply count 5 only, which is significant. But if there's a decimal point there, you count everything to be significant. Yes. So that's it for that one. We can talk about another rule for significant figures. So we are saying that in scientific notation or in standard form, all digits in the coefficient are significant. So in scientific notation, for example, if we have a number 6.0200 times 10 to the power 4, okay, so you know that this one has been written in standard form or in scientific notation. Or if we have a number like 3.050 times 10 to the power 4, even this one is in standard form. Or a number like 7.0 times 10 to the power 4, 7.00 times 10 to the power 6. Okay, then what we mean here is that in scientific notation, all digits in the coefficients are significant. So all digits here before times 10 to the power something, all digits there are significant. There before times 10 to the power something, these are significant. So for this one, we simply count 1, 2, 3, 4, 5. So it's 5 significant figures for that one. 5 significant figures. So for this one, it's 1, 2, 3, 4. 4 significant figures. So 4 significant figures. Then for this one, it's what? 1, 2. So 2 significant figures. Okay, then for this one, 7.00 times 10 to the power 6. So simply counting the number this side. So say 1, 2, 3. So it's 3 significant figures. Okay, so these are the rules when dealing with significant figures. Hope you have understood. Then let's also talk about the significant figures in calculations. Significant figures in calculations. Okay. Significant figures in calculation. How should we handle calculation? Significant figures in calculations. Okay, so how do we handle significant figures when carrying out calculations? Let's say when we are dividing, multiplying, we are adding or subtracting. How should we deal with significant figures? Okay, so let's talk about addition and subtraction. Addition and subtraction. So when you are adding or subtracting numbers which has to do with significant figures, for example, you are adding 2.01 plus 77.1. Yes. Then you're also subtracting 44.881 minus 22.486, like that. So let's try to carry out calculations so that we see how we go about them. Okay, so we have 2.01 there plus 77.1. What are we getting? That's 79.11. So see, this is giving us 79.11. Okay, then for addition and subtraction, the answer should be reported to the least decimal numbers of the what? Of what you were adding. So we're adding 2.01. This one has how many decimal places? So this one has 2 decimal places. Then 77.1, that is just 1 decimal place. So you will check which one has the least decimal places. So it is 1 decimal place. So this implies that the final answer should be reported exactly to 1 decimal place, 79.1. Okay, so that's a rule for addition and subtraction. So even subtraction we can do the same. We first check what we are subtracting. This is 44.81. So 0.81, that is 2 decimal places. Then 22.486, this is 3 decimal places. So when subtracting like that, the answer should be reported to the least decimal places from what we are subtracting. So the least decimal places, we have just 2 decimal places. Okay, so let's subtract. So we have 44.81, like that. Then minus 22.486. What are we getting? We're getting 22.324. Okay, so 22.324 should be reported correct to 2 decimal places, because this one has 2 decimal places. So say 22.32. I have reported that correct to 2 decimal places. So you have to round off to the least decimal place depending on what you had initially. So that's the rule for addition and subtraction. Hope you get the concept. Then what about what? For multiplication and division, how does it work? Okay, so let's say we are multiplying 14.03 multiplied by 6.1. We are also multiplying, let's say, 22.3 multiplied by 75.84. Okay, then let's say we are also dividing 14.03 divided by 6.1. Okay, so for division, we are saying that the answer for multiplication or division is rounded off to the same number of significant figures as in possessed by the least precise term used in calculation. So what we are using in calculation, we consider significant figures. For multiplication and division, consider significant figures. So here we are considering the number of significant figures. So this is 14.03 times 6.1. So in what we are multiplying, this is 14.03. How many significant figures are there? So that's 1, 2, 3, 4. So this is 4 significant figures. Then this is 1, 2 significant figures. So the answer should be reported correct to 2 significant figures. So let's multiply. We have 14.03 times 6.1. So we are getting 85. So it's 85.6. 85.583. 85.583. Now, if you check the least significant figures from what we are multiplying, we have 2, 6.1. So the answer should have 2 significant figures. So here 85.583, it's simply 86, 2 significant figures. Same applies here when you multiply 22, that's 22.3 times 75.84. So we are getting 1691.232. Then check this one as how many significant figures? It's 3, right? Then 1, 2, 3, that's 4 significant figures. So the answer should be reported to the least significant figures from what we are multiplying. That's 3 significant figures. So we should calculate 1, 2, 3 significant figures. So it's 1690. Okay, this is 3 significant figures. That one becomes the answer. Same applies to division. We have 14.03 divided by what? 6.1. We're getting about 2.3, and this one is exactly 2 significant figures. Okay, so that's it for this video. Hope you have understood.